Hi, in this video we'll be continuing the H2 Mathematics 2020 Paper 1. For question 10, it's a question on differential equations and mathematical modeling. So, like I've always said, mathematical modeling is when you convert English to math and it will probably be in some differential equation form. So, we just need to understand the English and be able to convert it to a mathematical model statement. So they say that every year has a death rate which is greater than the birth rate, and the difference between the death rate and birth rate is 3%. So write down the differential equation relating P minus and T. So obviously the change in population is the birth rate minus away the death rate. And we know the difference is 3%, but then the death rate is greater, so it has to be negative 0.03p. Then we are supposed to solve this differential equation to find an expression in P in terms of T. So we just do this. We see that we can just divide the P over, variable separable it, and then you integrate it normally. And you get that ln P equals to minus 0.03t plus C. Why didn't I put the modulus here? It's because the population has to be positive anyways. So P, you just bring the E up. So it's like EC E minus 0.03t. Then this EC is just a constant, so you just put A. Even if there is a modulus, when you bring the E up, this part will just become A again, because like EC is either positive or negative depending on whether the modulus you expect on is positive or negative. So then it'll just be A anyway, so it doesn't really matter. And this solves the differential equation because they didn't give you any initial condition, so you can't solve for A, so you just know it's a constant. But they asked you to explain what happened over many years. So when t goes to infinity, that's the definition of many years, e to the power minus 0.03t. Well, if you remember the curve, it will look something like that. So it will go to 0, so the population will go to 0 regardless of how big this A is. Just imagine your death rate always exceeds your birth rate, so you keep dying every year, more people. So obviously in the end the sheep population will go to 0. Now the scientists have wants to ensure the population of the sheep don't die, so they went to import more sheep at a constant rate of n. So it's just plus n in the end, and we're supposed to solve this differential equation. So in this case, now we don't just divide by p, we need to divide by this whole chunk. So then this part will be 1, you integrate it, and then this is what you should get when you integrate it. Then you just times the minus 0.63 up, you bring the E up, and you take out the modulus, so you just do it one fell swoop. And you can straight away write AE to the power minus 0.03t equals to minus 0.03p plus n. So you just bring the p over, bring this over, so you just n minus e a times e power minus 0.03t. Then when you bring this over, this minus sign disappears, so it's 0.03, so you divide by 0.03 and you should get this 100 times 3 times that then that expression over there. Then we're supposed to find the number of sheep, given that the sheep settled down after 500, settles down to 500 after many years. So many years again means t goes to infinity. We know that the population goes to 500, but as t goes to infinity, this part becomes 0. So this AE power minus 0.03t is 0. So actually 500 is just 100 over 3n. So n must equal to 15. Now the next question and the last question of this paper is a very, very long modeling question that tests your concept of application of differentiation in the end. So we are given a study and we are supposed to optimize the performance of the sport from fitness to technique. So a player scores 3 points by carrying the ball over the scoring line. So we just need to bring the ball over. And when the player scores this 3 point, extra point will be rewarded if it is kicked within C to D. The kick has to be any point along this line AB, where A is point at which the player crossed the scoring line. AB is then perpendicular to XY, so you get a lot of information, and CD is 4, XC is equals to DY. So this distance is the same as this distance. And we know that the point A is a distance A from C, so this is A. And A lies between X and C, so it's on this side, definitely. And we know that the kick is given at distance X away, so it's over here. And the angle is theta. So we have a lot of information, but it's generally easy to see it from the diagram itself what is meant. So now we're supposed to find the tangent theta. So tangent theta, well, very simply, theta is the angle where this big angle minus away this smaller angle to get theta. So tangent theta must equals to angle AKD minus away AKC. So when you plug it into the formula, it will be just you can expand out. Imagine this now, tangent theta equals to tangent AKD minus AKC. We got the formula to expand out, which is here. So it's angle AKD minus tangent angle AKC over 1 plus tangent AKD times tangent AKC. So we know what is tangent AKD. AKD is just opposite, which is A plus 4 over X. So it's A plus 4 over X minus A over X, which is AKC. You see, A over X. And then below is 1 over A plus 4 over X times A minus over X. So then we can combine this to become 4 over X. Below will just be this chunk. And after a few simplification, you bring the X down and everything, you should get 4 over X over X squared plus A squared plus 4A, which is this what we want to show. So this should be relatively clear. And moving on, now we want to maximize tangent theta. So we know tangent theta is this. So we just let tangent theta be like a y. So just imagine maximizing y. And how to do that? We need to differentiate and equate the derivative to 0. So we differentiate the whole term. You get this complicated looking thing, but you get to simplify it nicely to get this. And when we let the derivative equal to 0, this will be our end result. And we just minus 4x squared plus 16a plus 4a squared must equal to 0. So x squared must equal to a squared plus 4a. This means that you can square root it to get the answer and reject the negative side, since we know x has to be positive. Since x is like this distance, so it can't be negative. And then this means we just need to sub it into the tangent, and since we don't need to show its maximum, we assume that it will be maximum. So tangent theta, you just sub in as 4 bracket square root a squared a squared plus 4a over a squared plus 4a plus 4a plus a squared. So this is like 2 bracket a squared plus 4a. So yeah, the 4 and 2 will cancel, so we get 2 at the end. So this is the answer. Continuing, we know that a point of the x is called the optimal point. So it's the maximum tangent alpha theta. So why must you not choose to keep from this optimal point? It's because this optimal point maximizes theta. Okay, so we go nearer, it's definitely smaller theta, and we go further, it will also be smaller theta. But it might still be very far away from CD, so the accuracy of the goal might not be very good. So it's ideally to go closer to the goal. That will definitely increase the chance regardless of your theta angle. When theta is at the optimal, now we are supposed to show tangent KDA is this. Well, tangent KDA is what? KDA is this. And if we see from the graph, this tangent KDA is x over a plus 4. So x over a plus 4, we already know what is x. X is square root a squared plus 4a. So we can take out the a here and we can see that now this a plus 4 is just like square root a plus 4 squared. So you just cancel out. So you just get below to have square root, and here cancel this. Then we can combine the whole giant to be a giant square root. So it's square root a over a plus 4, which is what we want to show. And we're supposed to approximate the value when a is much greater than 4. Again, when a is much greater than 4, this part just basically reduces back to like, this part like a value will be very close to a, and this part is like a already. So this part is like square root 1. So tangent will be like close to 1. So this means that the angle will be close to pi over 4. Because tangent inverse 1 is pi over 4. And lastly, it is given that the length of the scoring line xy is 50. So when you go back to the diagram, this whole line is 50. We know that xc is and dy is the same length. So 50 minus 4, which is the middle portion, is 46. Then you divide by 2 to get what each xc or dy, which is 23. So xc is just 23. Then we know that xa now is 23 minus a. Because if you go here, xa is, this whole part is 23. Then you minus away this part. So you get this 23 minus a. So we know a has to be between 0, since it's positive, to 23. Because xa also has to be positive. So it can't exceed 23. So we got one condition for a already. Now we know that tangent theta must equals to this, which equals to 2 over square root a squared plus 4a. And this is strictly decreasing. Because as a increases, see, as a increases, this part increases, and that means this whole thing would be decreasing, so it's strictly decreasing. This means that tangent, the smallest value is when a is 23, so tangent has to be larger or equals to 2 over square root 23 squared plus 4 over 23, and the largest value is when 0, so it means it's unbounded at the end. So you just need to write the one-sided inequality, and then because tangent is also a strictly increasing graph, we just tangent inverse this whole thing, and we know that it will be bound. Because, okay, so the tangent graph looks like that. This pi over 2, like that. This minus pi over 2. So we know the unbounded part is the pi over 2, so we just need to find like this portion. So you just tangent inverse this value, which is 0.0801, and then this part we stick with pi over 2. So theta must lie within 0.0801 and pi over 2, and this part can be equal. So that's all for this question, and I hope you have enjoyed this series. This comes to the end of the paper. If you have any other further questions, any explanation you want me to go through, just leave it in the comments. I will answer them, as I've done so in previous videos. Please like, share and subscribe so that other people can view this video, and I'll catch you again. Bye.